This is my Precalculus course. Today we're going to prepare for the 4th exam of the course. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So I want to remind you, even though you're probably getting tired of me telling you this, you have to study in order to pass a math exam. And in order to help you study, we're going to do a practice test together right now, and I'm going to give you a practice test for homework as usual. Don't take the test in the next class unless you finish these practice tests. I know a lot of students will want to just go forward and take the test, and if you fail it, then you'll know that you were not prepared for it. Well, that's not the way it works in the academic world. If you want to succeed, you have to study for an exam. And so these practice tests are the absolute minimum that you need to prepare for the exam. So these practice tests are not optional. They're the absolute minimum that you need. If you want to get a really good score, you have to study all the things that we went over. These practice tests are just a way to get you started. So a graphing calculator is required for the exam. And as we do these problems, I want you to attempt them on your own. Don't just watch me do the problem. Attempt this problem, and if you can't do the problem, then what does that tell you? Well, it tells you you have to study these particular types of problems. That's one of the purposes of this exam, is to see exactly what you need to do to prepare for the test. If you can do this problem without any help, then what does that tell you? Well, it tells you you don't really need to study these as much as you would need to study other problems. So again, that's the purpose for this practice test, and the practice test I'm going to give for homework. So I want you to attempt this problem on your own, and if you get stuck, that's okay. We can do it together, but I want you to first see if you can do it on your own, and when you come back, we'll do it together. Okay, we're back. So we're supposed to figure out if we're supposed to figure out which one of these scenarios we have. So first we need to determine if the relation can qualify as a function, and we need to see if there's any repeated x values. If there's repeated x values, then most likely the relation can't qualify as a function. So we don't have any repeated x values. They're all different. So this can be a function. The next step is to determine if we have any repeated y values, and we can see we do have repeated y values. So even though this qualifies as a function, that doesn't mean that it can be a one-to-one function, and it's actually not a one-to-one function because you have two different x values producing the same y value. So I'm going to highlight that just so you can see what the crucial information is there. So now let's go to this second part here. Are there any repeated x values? There are no repeated x values, so this qualifies as a function. Are there any repeated y values? No, there's not. So that means that not only is this a function, but it's actually a one-to-one function. So if you got that right, good. So now let's see if there are any repeated x values. There are no repeated x values. That means that this does qualify as a function. And let's see if there are any repeated y values. And we can see that there are none. 0 is repeated, but I'm talking about just the y values. There's no doubles for the y values. So that means that this is not only a function, it's a one-to-one function. So if you got that right, excellent. And again, let's first see if this can qualify as a function, and we see immediately it does not qualify as a function because we have repeated x values. So this is not a a function. If you got these right, again, what does that tell you? It tells you that you may not need to spend a lot of time studying these types of problems. If you weren't sure how to do these problems, then that means you do need to spend time doing these problems. So again, we're accomplishing something by doing this practice test. Anybody who knows anything about the math curriculum knows that it's committing academic suicide to take a test without preparing for the test. That's especially true if we're talking about mathematics. So try number 2, and when you come back, we'll do it together. Okay, we're back. So we're going to switch the x and y values. That's all we're really doing here. If we're trying to find the inverse function, or a table that represents the inverse function, all we have to do is just switch the x's and y's. But there are some complications here, or there might be some complications. So we need to determine if this function is 1-to-1. Now I want you to be aware that we're assuming that this is a function, so we don't need to worry about whether or not it is or is not a function, because they call it f, and they say that the table represents a function. So we don't need to worry about whether or not it is or is not a function. We just need to determine if it's 1-to-1. Because if it's not 1-to-1, then the inverse function is not going to qualify unless we restrict its values. So we see here that this is actually not a 1-to-1 function. So that means when you find the inverse function, you see we have repeated x values, which means that this is not a function. It doesn't qualify as a function. So what we have to do is we have to omit certain values. We can omit these values, or we can omit these values. You can choose whichever omission you want. I'm going to choose to omit this one. And if I omit that one, I have to omit this point on the original function also, because we want these inverse functions to be perfectly matched. So that's one possible answer. Another possible answer is if you highlighted or circled these numbers. That's okay also. But I'm just going to do the ones at the end of the table. So if you got that right, excellent. So now let's switch these around. And of course we have to wonder whether or not we have a 1-to-1 function. And do we have any repeated y values? Well, no, we don't. So this is actually a 1-to-1 function. So that means that we don't have to worry about having to omit any values in the inverse function. So if you got those right, excellent. Okay, so try part 3. When you come back, we'll do it together. Okay, we're back. So this can be very confusing because we're using function notation. So what this information tells us, and I guess I'll write it over here. What this information tells us is that if you plug in an x value into the g function, then your y value is 2. All right? And so what that means is that if you plug in 2 to your f function, you should get -3. All right? Because g and f are inverse functions. So what this means is that f of 2, which is what we're looking for, is simply -3. So these problems are very easy. If you're used to doing these problems, then there's no tricks. These are very easy problems. But the notation is very confusing. And so that's the part that is going to give students some trouble. But if you got that answer, excellent. Again, if you got stuck, that's okay. This tells you that you need to spend some time studying those problems. in doing practice problems. So try part 4. When you come back, we'll do it together. All right, we're back. So this is really just the exact same problem. So we're trying to, well, first of all, if we plug in 5 into the f inverse function, we get -7, right? Well, that means if you plug in -7 to the inverse function, you should get 5 as your output. So what does that mean? Oh, and by the way, I shouldn't have highlighted both these. I don't know why I did that. I wasn't paying attention to what I was doing. So this tells us this information there, and this tells us this information there. So what are we looking for? We're looking for f of -7. So what this means is if you plug in -7 for the x value, what do you get for the y value? And that is 5. So that is the answer. Again, I know this notation is very confusing. Very, very confusing notation. But you're going to have to know it nonetheless. So if you got those answers, good. Try number 3. When you come back, we'll do it together. All right, we're back. So the mode is the number that appears the most, and so that is 81. The mode is just one way to measure the center of the data, or a most common number in the data, or the expected value. There's a lot of different ways to interpret that. So if you got that right, excellent. Try number 4. When you come back, we'll do it together. Okay, we're back. So this is a problem where we have to use what we call weighted average. If we take 412 and add 460 and divide by 2, that's not a weighted average, and it doesn't make any sense because you can't give these two numbers the same weight, because the plane was traveling 412 miles per hour for 5 hours, and it was traveling 460 miles per hour for 4 hours. So one's 5 and the other's 4, so it doesn't make any sense to just divide by 2. So we can't find the mean just by adding those two numbers. Now, the average speed, remember, is defined to be the total distance traveled divided by the total time that passed during that travel, or during the travel accomplished in that distance. So if we want to find the total distance, we have to, well, think about it this way. The plane is traveling 412 miles in 1 hour. That's what this green information tells us. The plane travels 412 miles in 1 hour. Well, the plane wasn't traveling for 1 hour, it's traveling for 5 hours. So what is the distance traveled in the 5 hours? Well, obviously it's just going to be 5 times 412. So that's the distance traveled during that first part of the flight. Well, then the plane speeds up and goes 460 miles per hour for 4 hours. So this number here represents the distance traveled during that time. And if you add these numbers up, you get the total distance traveled for the entire time. And then the easy part is just the total time passed, which is just 5 plus 4. So all we have to do is calculate that value. And I didn't give much room here, so we can do this in the calculator. 5 times 412 plus 4 times 460 equals 3,900, and then divided by 9 equals 433 and a third. So 433 and a third, and I'm going to write that down here. sorry, it's a little scrunched in here. And we have miles per hour. So that is the answer. If you got that right, excellent. Go ahead and try number 5. When you come back, we'll do it together. Okay, we're back. So you're going to need to remember for the exam what the difference quotient is. The difference quotient is f of x plus h minus f of x over h. You need to remember that. Now, I know you're going to say, well, how in the world am I going to remember this? I don't even understand why it's important. I don't want to remember it. Well, you just have to memorize it. You're going to learn as you go into calculus why that expression is particularly important. When combined with other concepts, it's actually the foundation of calculus. So you need to remember it at some point. And now's the time. So the difference quotient, which I'm going to label as dq, is equal to f of x plus h minus f of x over h, and we're just going to plug in. So these parts, the purple and the blue part, are the easy parts. I'm going to write them first. And notice it says we don't have to simplify. So all we have to do is just write an expression without really having to simplify. So h is the easy part. I'm just going to rewrite that. F of x is a fairly easy part because all that is just rewriting the expression as they gave it to us. X squared plus sine x minus 1. So that was really easy. That was just f of x. Now this is the part where students have trouble. F of x plus h. We're going to write the same thing here that we had here. It's the same expression as the blue expression, no difference whatsoever. Except instead of x, we're going to replace x with x plus h. So instead of x squared, we're going to have x plus h squared. Instead of sine x, we're going to have sine x plus h. And I can't forget to write my -1 there, but I ran out of room. So -1 there. That's part of the expression. So there you go. And again, you don't have to simplify the expression. So you can just leave that as your answer. Now, when you take your calculus course, your first calculus course, you're going to need to simplify that. But for these problems, we're just learning what the difference quotient is and how to write it. Okay, so if you got that right, excellent. Try number 6. And when you come back, we'll do it together. Okay, we're back. So the first thing we're going to do is just find the equation of the inverse. And remember, step 1 is to replace f of x with y. Step 2 is to change y to x and x to y. Step 3 is to solve for y. We want to get y by itself, so we're going to put the 3 in the other side of the equation. And then we're going to square root both sides. And remember, whenever you square root both sides of an equation, you have to write plus or minus. So that is the function. We just have to change the name to f inverse of x. But we have a problem here. You see this plus or minus? That's going to be a problem, because you can't call something a function if it doesn't pass the vertical line test, or if it has 2 outputs for one input, 2 different outputs for one given input. So in order to understand what's going on here, we're going to graph. So I'm going to graph this expression here. Now remember, f of x is the same thing as y, so I'm going to write it in this form, and then I'm going to subtract the 3 from both sides. Now the parent relation is y is equal to x squared, and I know that that is just a parabola with the vertex at the origin. If I subtract 3 from y, then that means I'm just moving the graph up 3 units. And we don't have to really show the scale. But that's what the graph looks like. I'm moving it up because we're subtracting 3 from y. So now we're going to find the inverse graph. Now remember, when you find the inverse graph, you reflect across the y-axis. But if you do that, it doesn't really change anything. So you just have the same graph. Then you rotate 90 degrees to the right. So it's the same for every graph. When you're trying to find the inverse graph, you reflect across the y-axis and then rotate 90 degrees to the right. So that means that we'd have a graph that looks like that. Something like that. You should probably graph that a little better. And your graph doesn't really have to be a perfect graph. So if you have kind of a messed up graph like I just drew, it's really not that big of a deal. The only point of this is to help you to understand what the restrictions need to be. So now you see this positive sign here? That's the upper part of the graph. You see the negative sign here? That's the lower part of the graph. You can't have both halves of the graph and call it a function. So what I'm going to do is I'm going to omit the bottom part. Now you can omit the top part if you want. You can omit whatever part you want. But I'm just going to do the bottom part there. Now we have to figure out what that corresponds to. Now if we go backwards and rotate up, or to the left 90 degrees, we see that that yellow part is there. And if we reflect across the y-axis, we see that the original function, the left part of the original function is a part that we omitted. So if we want these graphs to be, or these functions to be perfectly matched inverses, first of all, we have to omit part of this graph so that it passes the vertical line test, right? So that it can qualify as a function. But if we want them to be perfectly matched, and by the way, before I forget, let's go ahead and do that. So we need to erase this negative symbol. All right, so now it's just root x minus 3, not plus or minus root x minus 3. So now we've taken care of this problem. We omitted this part in our function. But if we want these functions to be perfectly matched inverses, we have to go back to the original function and erase the part that causes the problem. So what we need to do is put a comma here and write x has to be greater than or equal to 0. So we're going to restrict the original function so that the original and the new inverse function are perfectly matched, and that no aberrations will occur. Now, a lot of students might say, well, what about this part down here? Do we have to put restrictions on this part? Well, just looking at this expression, it's assumed that x can't be it's assumed that x can't be less than 3. All right. So you don't really have to state that. When we erase the plus or minus symbol, that got rid of this problem here. But anyway, long story short, that is our answer. So I know that that problem is kind of convoluted, but it's just something that you're going to encounter when dealing with the math curriculum. So you need to get used to this type of thing. Okay, so number 7 is the same type of problem. Go ahead and attempt number 7. When you come back, we'll do it together. Okay, we're back. So if we're going to find the inverse function, step 1 is to change f of x to y. Step 2 is to switch the y value to x and the x value to y. Step 3 is to solve for y. Now, if we're trying to look for the angle in a trigonometric function, we use special notation for that angle. It's sine inverse notation. Or you can use arc sine. Your calculator might have the arc sine notation. Okay, so then of course we change y to f inverse of x. Now the problem again is that we might have some issues with this function qualifying as a function. So let's draw the original graph. So the sine graph is going to look something like this. And then we're going to reflect across the y-axis. And again, it doesn't really make much of a difference if your graph is perfect. That's not the point of this. Then we're going to rotate 90 degrees to the right. Again, if you're trying to find the inverse graph, you always reflect across the y-axis and rotate 90 degrees to the right. You're going to have to memorize that for the exam. So again, my drawing here is not very good, but the graph would look something like that. But the problem is this doesn't qualify as a function. If you draw your vertical lines, I mean it fails the vertical line test, and that means that it's not a function. So we can't call it f inverse because f inverse implies that it's a function. So we have to omit values, and the typical values that are omitted are all these values here. And I'm going to use yellow because that's what I've used before. So we're only leaving that middle part there. So now when you show this expression, it's actually just assumed that the restriction that you see is applied. But we need to go back to the original function and omit the corresponding values so that they're perfectly matched functions. So what that means is that x needs to be between 90 degrees and negative 90 degrees. That's typically the way that it's done. And we're going to put a comma there. And you know, just to be thorough, we could say y has to be between negative 90 and 90 degrees. Now remember, with the inverse function, the y values are angles. I know that's kind of weird to think about that, but the y values are actually angles. Now, we didn't do that. We didn't write this part for this graph down here because, again, it's just kind of assumed that there are those restrictions applied. Here it's less obvious that there are restrictions applied, but here we know we can't plug in numbers that are less than 3. So we don't really necessarily need to show the restriction in the range. But if you did want to show the restriction in the range, then well, you could just write y, the range, has to be greater than or equal to 0. But again, this is not really necessary. And it's not really even necessary to write the range restriction here. Because again, it's implied when you see this expression. And it's traditional to have that restriction in the math curriculum. So if you got that right, excellent. Okay, go ahead and try number 8. When you come back, we'll do it together. Alright, we're back. So we're just going to use the change of base formula. So we have log base 6. We're going to choose base 6 because that's the base they tell us to use. Log base 6 of 9 over log base 6 of 2. And that's the answer. So we're done with that one. So it doesn't even tell us to calculate. We don't even have to calculate the value of the logarithm. We're just trying to show that we can write it as a base 6, or an expression with base 6 logarithms. Okay, so now we're trying to find the intensity, or we're trying to find the loudness given the intensity of the sound. So if you recall, the loudness is equal to 10 times log base 10 of 10 to the 12th times x. Okay, so that's the formula that we're going to use, and we're going to go ahead and plug in our x value. Our x value is 10 to the negative third power. So 10 to the negative third. And so we have 10 times, now notice that there's nothing written here. What is the base? Well, it's not written, but it's assumed that that base is 10. If you don't see a base, it's assumed to be 10. Very, very important. So now we're going to use exponent rule number 1. So I'm going to write that here. You don't have to write the Roman numeral if you don't want to, but... And we're going to add the exponents because we have the same base. So we have 10 to the 9th. Now we have to use our logarithm properties. You see how we have the same bases in these in this situation. So we need to go to this property here. See this property? We have the same base. We have a log exponential expression that is inside the log function. And the base of the log function is the same base of the exponential expression. So it just equals, the expression equals that exponent. So I know that seems kind of complicated, and by the way, you can get a picture of these. You're going to need to know, we did not use these, so you don't really need to know those. Let's see, I don't think I have any problems on the test that use these either, but those are all the logarithm properties that we have learned in the curriculum so far. Most of these I don't think you're going to need, but who knows, maybe on the next test I might have one problem, but I doubt it. So what that means is that this expression here reduces to just 9. Now that does not count the green 10 or the purple 10. It doesn't count that. So that whole blue expression becomes 9. It becomes whatever the exponent is equal to. So then we get 90, and loudness is measured in decibels. So D, capital B, and yes, it has to be a lowercase d and a capital B. So have you got that right? Excellent. Okay, so if you got that right, good. I want you to try part 3 of this problem, and when you come back, we'll do it together. Okay, we're back. So this is a complex number, and we can actually graph that number. Mathematicians have defined ways to graph complex numbers. I know that sounds kind of weird, but we can do that. So we're going to count 1, 2, 3 units out on the real axis because the real number is 3. And then we're going to count 1, 2, 3, 4 units down on the imaginary axis because this number is imaginary and it's negative. So that is the point. So we've got our point there. Let's make it nice and big so we can see, and that's really all you have to do for that problem. So if you got that right, excellent. Now I know what you're thinking. You're thinking, could it really be that easy? Well, yeah, those problems are not difficult at all. You just need to know how to graph the complex numbers. So try part 4. When you come back, we'll do it together. Okay, we're back. So you don't have to write the Roman numeral of the exponent rules that you use, but we just used Roman numeral 1, exponent rule number 1 again. We used it in a previous problem. When you're multiplying powers, you add the exponents. So now we're stuck. There's nothing we can do. I mean, we're just completely stuck here. Unless you know how to change an exponential equation to a logarithmic equation. So the exponent is equal to log base 10 of 3. This is just the notation that you use to find the exponent. It's not a trick. It's not anything that you need to worry about. It's just the notation that we use to tell our calculators to find that value, that exponent. That's all it is. But we don't use this notation. We use it for our calculators, but we don't use it. The reason we don't use it is because the calculator doesn't show the base when we have a base 10 expression, and that's the whole point of this. When you write base 10, log base 10, you don't write base 10, you just say log 3. It's assumed to be a base 10 logarithm. That may seem like a small detail, but if you don't know that detail, you're going to have a lot of problems. So, all we have to do is calculate log 3 divided by 7. And then we'll be done with this problem. Let me move this down a little bit. So let's go to our calculators, and we'll enter, well, I'm going to use the green alpha button on my TI-84 Plus. If you're using a calculator other than the TI-84 Plus, then you need to be aware that there's always a danger that when you're writing fractions, you're not going to use enough parentheses, or your calculator is going to misinterpret what you're doing. So please be careful. But if you're using a TI-84 Plus, it's going to be really easy because I can show you how to avoid this problem. If you're using a Hewlett-Packard or a Casio, that's fine, but you need to figure out how to bring up a fraction template. It's one of the most important things that you need to be able to do in your calculator. If you can't do that, then you're going to have some problems. So on the TI-84 Plus, I'm going to press the green alpha button and then the y equals button at the upper left. The stat plot F1 y equals button. Then I'm going to press the enter button, and now I have my fraction template. Okay, that's one of the most important things that you can that you need to learn how to do in your calculator. If you don't know how to do that, then you're not going to have the knowledge that you need to use that calculator properly. So now we're going to enter, or we're going to press the log button at the middle left, and notice it says log. It doesn't say the base of the logarithm, because if it's log base 10, then you just enter log. Then you're going to press 3, then the right parenthesis button. So you should have log 3 with 2 parentheses, and then over, and then you have your template here. You just want to push the down arrow key and then press 7. So now we should have 7 there. And then press enter, and you get, what should we round off to? It says to round off to the nearest hundredth. Remember, you're going to lose points if you don't round off correctly on the test. So 0.0, 0.07. Now, to be honest with you, that's not really enough, so I'm going to change that. Obviously, you're not allowed to do this on the test, but that's not really accurate enough. It's not realistic to have that level of accuracy. It's not very accurate. So we're going to say 0.068. So if you got that right, excellent. If you got 0.07, that's correct. You did it correctly. But I'm just going to change it. So just be aware that I actually changed that. Okay, so go ahead and try number 9. When you come back, we'll do it together. Okay, we're back. So the first thing we need to do is recognize this as a base 10 logarithm, because if we don't know what that notation means, then we might as well not even solve the problem, because we're not going to get anywhere. That's a base 10 logarithm. Then we need to solve the equation by isolating this logarithmic expression. This is a logarithmic equation, and to solve it, you simply isolate the logarithmic expression. So I added 10 to both sides, and I'm going to multiply both sides by 2. And so we get 22 is equal to log base 10 of x. So now I'm almost done. I'm almost ready to, well, I can just write the answer. Notice it says, leave your answer as an exponential expression. The reason for that is that this answer is going to be so big that it'd be kind of difficult for your calculator to write, to show you in standard form what this would look like. So remember, if we get to this point and we don't know how to translate back and forth between an exponential equation and a logarithmic equation, you can be sure that this is going to be the end of the problem for you. You're not going to get past that. So now we're going to translate to an exponential equation. This number here is the base. This number is the exponent, because that's what a logarithm is. It's an exponent. The logarithm is equal to the exponent. And whatever is in the log function, that goes on the other side of the equation, so therefore we're done. So we left our answer as an exponential expression because, again, that number is so big, we wouldn't want to write all those zeros. That would be a 1 with 22 zeros behind it. So if you got that right, excellent. Okay, on to part 2 here. So we have a polar equation, and it looks like negative 5 pi over 7. Well, obviously we have pi in our problem, and if you see pi as a multiple of a number that represents an angle, then that means that you're in radian units. It's assumed that you're in radian units. Now, technically, we can't assume that, but I just want you to know that that's just going to be the way it is. Whenever you see a pi there, it's assumed that we're talking about radian units, even though it is possible to show degree units with a multiple of pi. That's just never done. So I know that negative 7 pi over pi, or 7 pi over 7, is negative pi. Pi is 180, so it looks like this angle is a little less than negative 180 degrees. So that means it's going to be rotating out this way, and our line is going to look something like that. If we have a positive r value, we count out a certain number of units, and then we rotate negative 5 pi over 7. All right, we get our point here. But if we have a negative r value, we go out this way and rotate negative 5 pi over 7, and we get here. You connect the dots, and then you have your line. Doesn't matter what the r values are, the theta value is going to make it to where the points always land on the same line. But it's kind of hard to see all this. So what we can do is use our equation, tangent theta is equal to y over x. This helps us to translate or to convert back and forth between polar form and rectangular form of an equation. So we know theta is always negative 5 pi over 7. So we can just plug that in for the angle. Now at this point we need to go to our calculators, and again, the reason we're doing this is so we can see exactly what the line is going to look like. We could just convert this angle to degrees so we could get a better idea of what exactly it is. But it's better to convert it to a rectangular equation. So I want you to push the mode button on your calculator, because we need to be careful about what our angle units are. So use the down arrow key and make sure you're in radian units. So push the blue second button and then the mode button to quit out of that if you're using a TI-84 Plus. And then we're going to press the tangent button and then -5, and then I want you to push the pi button. There's actually a pi button. Push the blue second button and then the upside down V button, which is the exponent button. That's the pi button. If you push the blue second button before that pi button, you get your pi, and then divided by 7, and then enter. You don't have to put the end parenthesis. The calculator doesn't make you do that, even though it's not a correct statement unless you do. So we get approximately 1.25396 is equal to y over x. And if we multiply both sides of the equation by x, we get the following. So this kind of helps us get a better idea of what the line is actually going to look like. So if we plug in 0 for x, we get 0 for y, so we know that the point 0, 0 is on the graph. And then we can use the slope, because this equation just happens to be in slope-intercept form. Y equals mx plus b. B is 0 because there is no b over here. And this purple number is the slope. So we can use the slope. We can start at 0, that's the y-intercept, and then we can move up 1.25 and over 1. The reason we're moving over 1 is because you can consider the rise to be 1. Look at this purple slope here. You see that? We can write that number over 1. So the rise is 1.25396 and the run is 1. So we're going to go up 1.25396 and then we're going to go over 1. And then we can go down 1.256 and over 1 in the other direction, and we can just connect the dots. You can keep going as much as you want to get an accurate graph, but the graph doesn't really have to be perfect as long as you get the main idea. So that was part 2 of problem 9. And I know what you're thinking. You're thinking these problems have a lot of different parts to them. This is going to take forever to finish the exam. Well, most of the other problems, or many of the other problems, don't have multiple parts, so the other problems are not going to be as long. Okay, so number 10 is a problem that is a little different than the problems that we were given in class. I did not give you a problem that was exactly like this. This is a little different because it's asking you to determine whether or not these are inverse functions. So this problem is a little different. So I'm not trying to trick you, but we're at the point where you're studying for the exam and you're doing multiple practice tests, and it's important for you to be able to determine whether or not functions are inverses. And so again, I'm not tricking you by putting this problem on the test when it wasn't really something that it wasn't an exact problem that we covered. But since we're doing this practice exam, I want you to do this type of problem. So in order to determine if functions are inverses, we simply find the composite function, or an expression for the composite function. And if we get x, then we know they're inverses. If we get something other than x, then they're not inverses. So what this means is that we're plugging in g into f. Isn't it true that this is g? And isn't it true that we're plugging it in to f? So that's g. Okay, so now let's actually plug it into f. So f is x over 2 minus 2. Isn't that true? That's what x is, or that's what f is. We're going to plug in the green g into that. So it's going to be 2 times x minus 2. We plugged it in. So that's what that means. So now these 2's cancel out, and we're left with x minus 2 minus 2. And if we simplify, we get x minus 4. So these are not inverse functions. So we can just say no. If it were an inverse function, then we would just end up with x, not x minus 4. All right? So, if you got that right, excellent. But again, that was a slightly different variation of the problems that we saw in class. So, now you know how to do this for the test. But again, if you don't take these practice tests, then you don't know. So again, the practice tests are mandatory before you take the actual test. But problem number 11 is a problem that we saw quite a bit. So I want you to try number 11. Again, if you get stuck, that's okay. But attempt number 11, when you come back, we'll do it together. Okay, we're back. So in this problem, they tell us that they're inverse functions. And if they were not inverse functions, we couldn't call them f and f inverse. It just assumes with the notation that they're inverse functions. So we're assuming that they are inverse functions, and we're asked to show how we know that. So we have to find f of f inverse of x, just like we did up here, except we're calling this f inverse instead of g. So we're going to plug in log base 4 of x plus 7 over 9 into the function f. So I took this green function here and I plugged it in there. That's f inverse. And I plugged it into f. And you know what? I probably should use blue. Okay, so we have 9 times 4 to the x minus 7. So this is f. And we're raising that to the log base 4. I'm going to move this down. Raising it to the log base 4 of x plus 7 over 9. And then I can't forget to subtract 7 there. So again, that is the green function. So I plugged in the green function into the blue function. The blue function is f. You don't need to use all these colors when you do the test, obviously, but the colors are just to show you what's happening here. So now let's simplify and see if we get x. If we get x, that means that they're inverses. So we need to use an exponent rule here. We're raising a logarithm, and notice that these numbers here, the bases are the same. So that's this property here. So the expression just becomes whatever's in the log function. So this entire expression here becomes x plus 7 over 9, and the logarithm just disappears. So now we're multiplying, but these 9s cancel out. And not only do the 9s cancel out, but the 7s cancel out, so we got x. So what does that prove? It proves that they're inverse functions. But just to be thorough, we're not only going to simplify f of f inverse of x, but we're also going to simplify f inverse of f of x, just to make sure that these are inverse functions. So now we're going to go in the other direction. We're going to plug in the blue function into the green function. So this is going to be f inverse with the blue function plugged in. So that means we're going to have the green function on the outside, but we're going to have the blue function on the inside. So I know I'm kind of writing small here. Okay, so we've got the green function on the outside and the blue function on the inside. Again, you don't have to use colors. So let's simplify. I'm going to try to make a little more room here. So these 7s are going to cancel out, and we're left with log base 4 of 9 times 4 to the x over 9. And by the way, you don't have to show every step of this, just show a few steps. The 9's cancel out, and we have log base 4 of 4 to the x. And remember, we talked about this principle. If these bases are the same, then the expression is just equal to whatever the exponent is equal to. So we're left with x. So again, that proves that the functions are inverses. We're now even more sure than we were before that the functions are inverses. So if you got that right, excellent. But we're still not done yet, because we have to write something to conclude this process. We can probably just write a big check for each one of these. Okay, if you got that right, good. Try number 12. When you come back, we'll do it together. Alright, we're back. So if you want to find the point where the graphs intersect, then we just set the y values of the functions equal to each other. Or we could set the x values equal to each other, but why would we want to do that? That would be very difficult. We'd have to solve for x in both of these equations, so that would not work very well. So we're going to set the y values equal to each other, because if these two graphs intersect, and that means they have points in common, and we want to know what those points would be. If the points have the same coordinates, then obviously the y values of the coordinates are equal. So remember, f of x and g of x, that's the same thing as the y value of the corresponding coordinates. So we have x squared plus 12x minus 27 is equal to 2x squared. Now, you should recognize this as a special equation. If you don't recognize it, then that means there's no way you're going to be able to solve it. One of the big problems that students have is they don't recognize this type of equation, and this type of equation requires special methods to solve, but if you don't know what type of equation it is, you can't use those special methods. This is a quadratic equation, and remember, if you have a quadratic equation, in order to be able to solve it, you have to put it in standard form. So that's the next thing we need to do. So we're going to put everything on the right side of the equation. So I subtracted x squared from both sides, subtracted 12x from both sides, added 27 to both sides. And remember, we need to write our zeros. So now it's in standard form, and now I can solve it. There are multiple ways to solve a quadratic equation. One way is with the quadratic formula, but we only use that if we can't factor. In this problem, we can factor, so the other method is factorization. I know that I can factor because I can find two numbers that multiply to 27 and add up to negative 12. So that's going to be 9 and, or negative 9 and negative 3. So now, this tells us that if x is 3, or if x is 9, then the graphs are going to intersect. But now we need to actually find the coordinates, because it says to find the points, or the coordinates of the points. We have the x values, but we don't have the y values. Now, because these are x values that make the y values equal, in order to find the y values, the corresponding y values for these x values, you don't need to plug them both into f of x and h of x. You can just plug it into one of the easier equations. It's a lot easier to plug it into h of x rather than to plug it into f of x. So I'm going to use h of x. I'm going to say x is 3. And then we have 2 times 3 squared, which is 2 times 9, which is 18. So now our point is 3, 18. So that's one of the points. Now I'm going to plug in 9 to h. Again, you don't want to plug it into f, because f is a much more complicated equation. So h of 9 is equal to 2 times 9 squared, which is 2 times 81, which is 162. So the point that we're looking for is 9, 162. So those are the points where the graphs intersect. So if you got that right, excellent. Okay, so go ahead and try number 13. When you come back, we'll do it together. All right, we're back. So our equation is A is equal to P e to the RT, and it says the investment starts at 1,029 and it grows to 28,000, and this occurs over a period of 25 years. So it's traditional to write the 25 before the variable. And then we're going to solve this basic exponential equation. This is a basic exponential equation, and you want to solve it by isolating the exponential expression. And we're going to do that by dividing both sides by 1,029. So 28,000 divided by 1,029 is some number that we need to keep in our calculators. So I'm going to write ... which means keep that in your calculator. So then at this point we're stuck, because we don't know how to solve this unless we know how to translate an exponential equation into a logarithmic equation. So remember, we have to use logarithm notation. The exponent is equal to log base, whatever the base is, and in this case it's e, of that number there. And I want you to keep that number in your calculator. That number should still be in your calculator. A number that's not rounded off. So that's how we tell our calculator to find that logarithm. It's just a notation that we use. But actually we don't use that notation. When your base is e, you use ln. So it's ln. You don't have to write this step if you don't want to. You can just go straight to ln. So now we need to do one more step here. We need to divide both sides by 25. So r is equal to ln 27.21088. Keep that number in your calculator, divided by 25. So I'm going to push the ln button in my TI-84 plus. And if you want, you can push the up arrow key to go to that number that you still have in your calculator and highlight that and press enter. It'll put it right in there for you. Or you can push the blue second button at the upper left and then the negative symbol with parentheses around it at the bottom. And then you should have ln of your answer. There's multiple ways to do this. Okay, so then I'm going to press enter, and we get 3.3036 ... over 25, but then I'm going to divide by 25, and then r is going to be approximately, because we're going to round off, approximately equal to 0.1321, and actually I guess I don't have to round it at that stage. We can just put ... meaning it keeps going, but we need to round to the nearest hundredth of a percent, and so that actually means that we need more digits. And then we can put a ... So if we change this to a percent, it's going to be 13.2144%, so on and so forth. But we need to round to the nearest hundredth of a percent. So what that means is after you change it to a percent, then you find the hundredth place and ask, do you round up or down? And of course we round down. So you better be ready for that on the test. Rounding to the nearest tenths or hundredths or thousandths of a percent is different than just rounding to the hundredths or tenths or thousandths. If it says round to the nearest hundredths of a percent, that means that after you change to a percent, then you round to that accuracy. So it's very important that you understand that. Okay, if you got that right, excellent. On to number 14. If f of x is equal to this expression and f of k is equal to 2, find k. So try number 14. When you come back, we'll do it together. All right, we're back. So the problem tells us that f of x is equal to the square root of 4x plus 1 over 2 minus 8. If that's true, then that means that f of k is equal to the square root of 4 times k plus 1 over 2 minus 8. All right? But they tell us that if you plug in k to the function, you get 2 as your output. So we plugged in k to the function, and the output should be 2. So I'm going to change this to 2. So now it's asking us to find what k is. Well, how do we do that? Well, obviously, we just solve the equation. So this is an equation with the square root. We're going to isolate the square root to solve the equation. So we're going to add 8 to both sides. You don't have to show every single step of the algebra. You need to show some steps, but not every step. Multiply both sides of the equation by 2. Then we're going to square both sides of the equation. You don't have to show the squaring like I'm showing here. You just have to show the result after you're done squaring. So then we get 400 is equal to 4k plus 1. Subtract 1 from both sides. Divide both sides by 4. Again, I'm showing way more steps than I really need to here. But that is the k value. So if you got that right, excellent. Okay, go ahead and try number 15. When you come back, we'll do it together. All right, we're back. So the problem tells us that f of x is equal to negative 6 over 1 minus 3x. If that's true, then that means that f of n is equal to negative 6 over 1 minus 3n, because you're just plugging in n for the input. But they tell us up here that if you plug in n for the input, you get negative 1 for the output. So we can just change that to negative 1. Then we're asked to find n. Well, how do we do that? Well, obviously we just solve the equation. So is this confusing? Yeah. Do you still have to do it? Yes. So there's a lot of different ways to solve this equation. And students will typically get really confused and frustrated because teachers will use different methods, and if you're not familiar with a particular method that your teacher is choosing, you'll get frustrated. We don't have time to show every single method, but I'm just going to quickly go over some different methods. So you can consider this to be negative 1 over 1. Then you can flip both sides of the equation, and if you do that, you'll just get negative 1 on the left side, and you'll get negative 1 minus 3n over 6. Now this equation is a lot easier to solve than this equation. So you can just multiply both sides by 6, cancel out the 6 in the denominator, and so on and so forth. That's one way to solve it. Another way to solve it is to multiply both sides of this equation by 1 minus 3n. And by doing that, you get rid of the fraction. That's typically the way that I would do it in my head. That's just the way that I've always done it. And these cancel out. And so it gets rid of the fraction. That's the benefit of that. Because you might be thinking, well, what does that do for us? Well, it just gets rid of the fraction. It's a lot easier to deal with the problem if you don't have a fraction. And let's see, another way to do it, which is really not practical at all, but it's the way that it's actually easiest to understand, is you can change this to a fraction and then multiply both sides by 1 minus 3n. That's actually the way that I taught in my beginning algebra course, because it shows in a very systematic, simple way how to solve the problem. But that's not really practical when you get to upper mathematics, because it just takes too long. You have to write a lot. The reason that this method works is because you're going to have the same denominator, which means that the numerators are going to be equal to each other. So you can use any method that you want to use. So I'm going to multiply both sides by 1 minus 3n. And then I'm going to distribute the negative. Then I'm going to add 1 to both sides. Then I'm going to divide both sides by 3. So we get negative 5 over 3. So if you got that right, excellent. Okay. Go ahead and try number 16. When you come back, we'll do it together. Alright, we're back. So step 1, to find an inverse, or the equation of the inverse function, we change f of x to y. And the only reason we do that is just to make it easier to rewrite the expression. This notation is kind of difficult to have to constantly rewrite, and it's very confusing notation. Doing operations with that expression can be kind of confusing. So that's step number 1. Step number 2 is we're going to change y to x and x to y. Step number 3 is we're going to solve for y. So we're going to get y by itself on one side of the equation. So we're going to subtract 4 from both sides of the equation. Then we're going to multiply both sides of the equation by negative 3. then we're going to, well, at this point we're really stuck. There's nothing we can do unless we know how to translate an exponential equation to a logarithmic equation, because we're looking for the exponent. So y is equal to log base 5. That's just what you write whenever you're trying to find an exponent using a calculator. Log base 5 of negative 3 x plus 12. I'm going to go ahead and distribute the negative 3. In fact, I should probably do that before I convert to a logarithmic equation, just so it doesn't confuse anybody. So we have negative 3x plus 12 is equal to 5 to the y power. And we need to use parentheses. If you don't use parentheses, then it's not going to be a correct expression. So very important to use parentheses in a logarithm. So that is the inverse function. But step 4 is to change y to f inverse of x. Remember, that's the typical notation that we use for an inverse function. Now, you might be thinking to yourself, well, wait a second, do we have to have any kind of domain restrictions here? You're only going to see that with problems where I'm going to warn you, like these problems that we did earlier. See all this information here, I warned you about that. Unless I warn you, you can assume that you're not going to have any of those problems. So I'm making the problem easier for you. If you graph this function, you can see that it's a one-to-one function. It not only passes the vertical line test, it passes the horizontal line test. So if it's a one-to-one function, then that means when you reflect across the y-axis and rotate 90 degrees to the right, and you get this graph, you can see this graph passes the vertical line test. So this is a function, so we don't have to worry about any problems. Again, I know that this is very complicated stuff, but you don't have to worry about that for this problem. So if you got that function, good job. Try number 17. When you come back, we'll do it together. Alright, we're back. So step 1 to find the equation of the inverse function is to change f of x to y. Step 2 is to change y to x and x to y. Step 3 is to solve for y. So we're going to subtract 7 from both sides. I want to divide both sides by negative 3. And then we're going to cube root both sides of the equation. Now you don't have to show this. You only have to show the result after cube rooting, but just to be clear what's happening here, I'm going to go ahead and show the cube rooting. Okay, so we're cube rooting everything, and so we have y is equal to the cube root of x minus 7 over negative 3. Now you might say, well, wait a second, don't we have to put a plus or minus symbol here? And the answer is no, because this is an odd index. You only have to write a plus or minus symbol if you have an even index, like 2, 4, 6, 8, 10, 12. If you have an odd index, like 3 or 5, 7, 9, 11, so on and so forth, you don't have to write a plus or minus symbol. So step 4, the last step, is to change y to f inverse of x, because we found the inverse function. Remember, the inverse function is a function that does the exact opposite, or you could say that it undoes what the other function does. And again, you don't have to worry about domain restrictions for that problem. So if you got that right, excellent. Okay, go ahead and try number 18. When you come back, we'll do it together. Okay, we're back. So you don't have to graph this function, but just to show you what's going on here, I'm going to go ahead and graph it. Now remember, f of x is y. You can just consider it to be y. Now the parent function, or the parent relation, whatever you want to call it, is y is equal to absolute value of x. And if you were to graph that function, it would look something like this. It's not a perfect graph, but something like that. Now, if the function we're trying to graph is this function here, if you add 2 to both sides of the equation, you see that the purple equation and the red equation are exactly the same. The only difference is you're adding 2 to y. So that means you're going to move the graph down 2 units. So that gives us an idea of what the graph looks like. And technically I have to keep these arrows going up so I can fill up the window. But this, again, this is not, it's not required that you graph this. We're just graphing so you can see what's happening. So the average rate of change is the slope of the line going through the 2 points on this graph that we're considering. So x equals -1. That would be about here. Now, if you plug in -1 for x, absolute value of -1 is 1, and then 1 minus 2 is -1. So I know that the point is -1, -1. If you plug in 1 for x, then you get absolute value of 1 is 1, 1 minus 2 is -1. So 1, -1, -1. So these are the 2 points that we're considering. The average rate of change, again, is the slope of the line going through those 2 points. So what is the slope of that line? Well, it's a flat line. It's a horizontal line. So we know the answer is going to be 0. So that just gives you an idea of what we're doing here. But let's prove it algebraically. This is the part of the problem that you actually have to do. So the slope of a line is equal to the difference of the y values divided by the difference of the x values. We learned that in my beginning algebra course. And but when you're dealing with functions, you're going to have f of x2 minus f of x1 over x2 minus x1. So instead of y2, we write f of x2. Instead of y1, we write f of x1. It's the same thing. It's just function notation. And this stands for the average rate of change. You can call this whatever you want to call it. You can call it the slope of the secant line. Sometimes you may see it as with a SE, just meaning slope of the secant line. Or you can just call it the average rate of change. You can actually spell it out. So what we're doing here is we're plugging in 1, and we're plugging in -1. All right. So -1 that went there, and 1 that went there. These are the same values that we have up there. So now we actually have to calculate f of 1. To do that, you'd plug in 1 to this function. So absolute value of 1 minus 2, that's the green f of 1. You don't have to show every step like I'm showing here. You can actually do a lot of this in your head. Then we have absolute value of -1 minus 2. That's the blue value there. And then we have a double negative, so we have 1 plus 1. Sorry, my computer's going kind of slow. Okay, so now we have to calculate the green expression. The absolute value of 1 is 1. 1 minus 2 is -1. The absolute value of -1 is 1. 1 minus 2 is negative 1. Add those two yellow numbers, we get 2. And then we get negative 1 minus negative 1, which is negative 1 plus 1, over 2. And so we get 0 over 2 is equal to slope, average slope, and 0. So that's the average rate of change of that function over that interval negative 1 to 1. So you don't have to graph it. You don't have to show every single one of these steps. But you do have to show a few of these steps, and you have to show, obviously, the answer. So if you got that right, excellent. Okay, try number 19, and when you come back, we'll do it together. Okay, we're back. So the problem tells us that f of x is equal to negative 3x squared plus x plus 3. If that's true, then that means that f of p, and that's a capital P, so I should probably make this a capital P too. If that's true, then f of p is equal to negative 3p squared plus p plus 3. Alright, that's just the definition of the function. But they tell us up here that f of p is negative 3. So that means if the input is p, then the output is negative 3. So I just changed f of p to negative 3 because we plugged in the p value. So our input is the blue and our output is the green. So what are we trying to find? Well, we're trying to find p, and this information helps us to do that. So now all we have to do is solve this equation, but there's no way that we can possibly solve this equation unless we recognize the equation as a quadratic. If you want to solve a quadratic equation, you have to put it in standard form. We could put everything on the left side of the equation, or we can put everything on the right side of the equation. It doesn't really matter. In this particular case, normally you want the p squared term to be positive if you're factoring, but we're not going to factor. If you try to factor, you're going to find that this is not really easily factored. So we can't solve this unless we have our special tool, the quadratic formula. One of the most important things that we learn, which represents the culmination of most of the math curriculum in high school, and that is the quadratic formula. So this is how we're going to find p. So b is this number here, c is that number there, and a is this number here. So we have negative 1 plus or minus root 1 squared minus 4 times negative 3 times 6 over 2 times negative 3. So A went there, and C went there, and B went here. Okay, so now we just have to simplify. So we have negative 1 plus or minus root 1 squared is 1 minus 4 times negative 3 times 6. So we're going to have minus 72, it looks like, or minus negative 72. You can simplify this in a lot of different ways, in a lot of different steps. but it's going to be a double negative. So we're going to get 73. So we have root 73 over negative 6. Now, remember, if we multiply both sides of the equation by a negative, we get 1 plus or minus root 73 over 6. So this is a lot simpler to write it that way. If you multiply the denominator by a negative 1, you get 6. If you multiply the numerator by negative 1, you distribute to each of these. The negative 1 becomes positive 1. And the plus or minus doesn't change because if you multiply a plus or minus by a negative 1, it doesn't really change the outcome of the situation. So those are the answers. There's actually two answers. Either of these answers work. 1 plus root 73 over 6, or the other answer that works also is 1 minus root 73 over 6. So if you got that right, excellent. Okay, let's try number 20. Go ahead and attempt number 20. When you come back, we'll do it together. Okay, we're back. So the first thing that we need to do is recognize this logarithm as log base e of x. That's what that actually means. Now we're going to solve this logarithmic equation by isolating the logarithm. So we're going to add 4 to both sides. And then we're going to divide both sides by 2. And at this point we're stuck unless we know how to convert to an exponential equation. So remember, the base is that little subscript there. The exponent is what the logarithm is equal to, and whatever's in the log function goes on the other side. Now it says round to the nearest thousandth, so we can't leave our answer like that. So how do we do this? Well, we can't write our answer because we don't even know what e is, but luckily our calculator does. If you press the blue second button on your TI-84 and then the LN button and then enter 1 and then press the enter button, you can see that e is equal to 2.71828 and so on and so forth. That's what e actually equals, but we don't want to raise it to the first power. We want to raise it to the 6th power. So push the blue second button and then the LN button at the middle left and then enter 6, and you should have e to the 6 in your calculator, and it says to round to the nearest thousandth place. So we're going to have 403.429. So we got that right. Excellent. All right, go ahead and try number 21. Be aware that we need to use radian units for number 21. That's the whole point of that problem. You have to use radian units. So make sure that your calculator is in radian mode. Press the mode button and go ahead and try number 21. All right, we're back. So I'm going to let theta equal 0. Now notice I don't write a degree symbol here because I'm not using degrees, I'm using radians. So r is equal to 2 over 3 plus sine 0, which is 0. So r is equal to 2 over 3. So 2 over 3, comma, 0 is our first point. So let's count out 2/3 and then rotate 0 degrees, and we get our point is approximately there. Okay. So now let's choose another theta value. Let's choose pi over 2. Now again, we have to use radians. Radians for our angle units. So 90 degrees is pi over 2. So if we plug in 90 degrees, what do we get for sine? Well, sine is going to be 1. And if we simplify that, we get 2 over 4, which is 1/2. So the point that we're looking for is 1/2 comma pi over 2. All right. Okay, so let's plot that point. We're going to move out 1/2 on the x-axis. I want to move this point over a little bit, a little bit over to the right. So we're going to move over 1/2 out on the x-axis, and then we're going to rotate 90 degrees, and that's going to get us to precisely there. Okay. So now let's maybe try negative pi over 2, so negative 90 degrees. So r is equal to 3 over 2 plus sine of negative 90. So sine of negative 90 is negative 1. So r is equal to 1. And the point that we're looking for is 1 negative pi over 2. So 1 negative pi over 2. So we're going to count out 1, and then we're going to rotate negative pi over 2, which again is negative 90 degrees. Okay, so now what should we try? How about pi? Remember, you'll notice I'm using quadrantal angles, angles that are multiples of 90 degrees, because that just makes it easier. So let's plug in pi. Sine pi is 0. So we have 2/3 comma pi. That's the point that we're looking for. So we're going to move out 2/3 and rotate pi radians, and we get about there. So at this point, it looks as though we might be seeing what the shape is going to be, but we don't really know. So we need to use our calculator. And again, you want to press the mode button and make sure you're in polar mode. See, it says function, parametric, polar, POL, polar. And you want your angles to be in radian units. Now push the y equals button. Enter this function into your calculator. And you can use the green alpha button to use the fraction template, the green alpha button, and the y equal button at the upper left, the stat plot F1 button. Use the fraction template. And you want to press the window button and make sure that your theta min and theta max are in radian units. You want negative pi and positive pi. It's probably a good place to start. Or you can maybe do negative 2 pi and or positive 2 pi. It's also important that you change your step. If your step is in degree units, usually we use 1 degree for a step, but that's not going to work for radians. We need maybe about 0.1. Or, well, 0.1 is probably okay. And make sure that your window is something like this. You want your minimum x value to be negative 2, your maximum x value to be approximately 3, your minimum y value to be negative 2, and your maximum y value to be about 2. And then press the graph button. Now on the TI-84 Plus, you're going to see something that kind of looks like a circle, but remember the TI-84, it kind of has an issue when it comes to graphing with the window. It doesn't really show the graph the way it's supposed to be. It kind of warps the window. So just be aware that this is supposed to look like an ellipse. And my graph, as you can see, is not perfect, but Your graph doesn't have to be perfect, so don't worry about it. If you got that graph, good job. And we need those points also. Remember, those coordinates are part of the answer. So if you don't write those coordinates, then you're going to lose points. Okay, so on to number 22. Go ahead and try 22. When you come back, we'll do it together. Okay, we're back. So there's two parts of this problem. One part is going to be where we find the k value. We need k. And we're going to use the half-life to help us find k. So if the half-life of lead-210 is 22.2 years, then what that means is if you start with A0 grams of the material, then you'll have 1/2 of A0 after a certain period of time. And that time we're actually given is the half-life. It's 22.2 years. So this information comes from this simple statement here. All right. But now notice what we can do. We can just divide both sides of this equation by A0 and just get rid of the A0. Sorry, my computer's going kind of slow. Divide both sides by A0, and then we have 1/2 equals e to the 22.2 k. Okay, so now we need to solve this basic exponential equation, and I just want to keep reminding you that you cannot solve this equation unless you know how to translate back and forth between an exponential equation and a logarithmic equation. Obviously, we can't solve this equation in our heads, so we need to use a calculator. But what notation do we use for the calculator to find the exponent? Log base e of 1/2. Make sure you put the 1/2 in parentheses. The base is always this subscript here when you write the logarithm. So again, this is just a notation that is entered into the calculator to help us find the exponent. But actually, we don't use that notation. We use ln. When the base in a logarithm is e, we always abbreviate the logarithm with just ln. So now we can divide both sides of the equation by 22.2, and we're going to need our calculators for this. So you want to press ln, and then you can just enter 0.5 for 1/2. Enter. And so we get negative 0.693, and it just goes on and on, divided by 22.2. Then we can just enter divided by 22.2 and then enter. So we get negative 0.03122, and it just goes on and on. You want to keep that in your calculator. So that was part 1 of this problem. We were given the half-life, and that enabled us to find our k value. The k value is called the rate of decay. Now, why is the rate negative? The rate is negative because this is talking about decay. If we were talking about growth, the rate would be positive. Okay, so now we go on to step 2. Step 2 is to use our equation to find out how much material is going to be left after 100 years. So we're going to plug in 100 for T. Our initial amount is 0.45 grams. We know our K value is negative 0.03122 ... Again, you want to keep that in your calculator. The T value is 100. So now we have to simplify that expression. So I have this number in my calculator, and then I'm going to enter times 100, and then enter. So I get e to the negative 3.1222 dot dot dot, and I can press the blue second button and then the ln button, and I should have e with a little space there, and I can use the up arrow key to go to that previous number and then press enter, and it'll put it right in there for me. Or I can just press the blue second button and then the negative symbol with parentheses around it at the bottom right. So then you should have e to the negative 3.12222 in your calculator. Press enter, and then we get 0.04405 dot dot dot. Keep that number in your calculator and then multiply by 0.45 times 0.45, and we're going to see how much of, or how many grams of this stuff is left after 100 years. Looks like we're going to have 0.02 grams, because it says to round to nearest thousands. Alright, so if you got that answer, excellent. So this was the blue part. That was part 2. Okay. So all that information was plugged in here. Okay, so go ahead and try number 23. There's 2 parts to number 23. When you come back, we'll do it together. Okay, we're back. The carrying capacity for this type of logistic growth model is always this number up here, this blue number. So 156,213 bacteria. Carrying capacity means the maximum number of organisms that can exist in this particular environment or this colony. So the logic behind that is that, well, this purple expression here, because it has a negative exponent, it's actually 1 over e to the 0.2 t. So these purple expressions are the same thing. They're the same. They're equal to each other. So if you look over here at this fraction, you can see that as t gets bigger and bigger, this fraction actually approaches 0. And if we let t get really, really big, for all intents and purposes, we can just assume that the purple expression here just goes to 0. And 0 times 19 is 0, and then we're left with 156,000 over 1 as the maximum population. So again, that's why that works. Okay, so now what is the initial population? Well, that's just whatever the population is when the clock is set to 0. So we're going to write that expression. And we're going to plug in 0. 0 for t. Now you can do this in your calculator. You don't really need to do it in your calculator because you can actually do it in your head. But I'm going to show you the steps just so you can understand the math. So negative 0.2 times 0 is 0. But e to the 0 power is 1. Remember, anything raised to the 0 power is just considered to be 1. That's exponent rule number 7. So then we have 156,213 over 1 plus 19, and we don't need to show every single step, but we would then get 156,213 divided by 20, which is, well, you can round. It doesn't say really what to round to, but we can just round to the nearest bacteria. So we have 7,811 bacteria. All right, so if you got that answer, good job. Okay, so go ahead and try number 24. Number 24 asks you to use this same equation. So try part 1 of 24, and when you come back, we'll do it together. All right, we're back. What will the population of bacteria be after 5 hours? So we're going to just plug in 5 into our previous equation that we were using. Again, this is called a logistic growth model. So let's make sure we have that correct. It looks right. So notice I plugged in 5, the blue 5, and we can just enter this into our calculator immediately. We don't have to show every single step. So I want you to well, if you have a TI-84 Plus, it's going to be easy. But if you don't have a graphing calculator, it might be tough to plug this all into your calculator in one step. You can reference this information if you need some help with the algebra. I'm going to push the the green alpha button and then the y equals button. Then I'm going to press enter, and you should get a fraction template that looks like that. Then I'm going to enter 156,213 in the numerator and use the down arrow key and enter 1 plus 19, then the blue second button, and then the ln button. So what you should have at that point in your calculator is 156,213 divided by 1 plus 19 e to the box. In the box, you're going to enter negative 0.2 times 5 and press enter, and you have your answer. So we get approximately 19,552 bacteria. You can round to the nearest bacteria, because it's kind of hard to say we have a fraction of a bacteria. So if you got that right, excellent. Okay, so now I want you to try part 2. Part 2 doesn't really have anything to do with part 1. Try part 2 of 24. When you come back, we'll do it together. Okay, we're back. So let's say that our calculator doesn't have the ability to compute any base logarithm. So we have to use base 10 or base e, because calculators that are not very sophisticated, they only do base e and base 10 logarithms. Most calculators today can do any base, but a lot of them don't. So what do? Well, we can write natural log 14 over natural log 3, or we can write log base 10 of 14 over log base 10 of 3, because these are base 10 logarithms and these are base e logarithms. So you can do either one. Which one do you want to do? It doesn't matter. I'm just going to choose natural log 14 over natural log 3. You'll get the same answer no matter what. So in your TI-84 Plus, you can press the green button, then the y equals button at the upper left, and then enter, and then ln 14 down arrow key, ln3 and then enter. And we get approximately 2.402. So if you got that right, excellent. Okay, now we have one more problem. Go ahead and try 25. When you come back, we'll do it together. Okay, we're back. I'm going to say 14.626 because the problem doesn't tell us what to round off to. And that's going to be days. So if you got that right, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3, number 4, number 5, 6, 7, and 8. But don't go before you get your homework. Remember, the homework is a practice test. So here's screenshot number 1 of your homework. This is practice test version 2. You did version 1 just now. We did that together. Here's screenshot number 2 of the practice test version 2. And screenshot number 3, number 4, number 5, and 6, and 7, and 8. But don't go before you get the answers to the practice test. Remember, it's not enough just to attempt the practice test. You must do it correctly. So here's the answers, or numbers 1 through 16. So get a shot of those answers, and here's the rest of the answers. Be sure that you did every problem correctly. If you did one of them wrong, go back and figure out what you did wrong so that you can be prepared for the exam. Again, the practice tests are mandatory before you take the test in the next class. So get that practice test done, and I'll look forward to seeing you in the next class.